Hello and welcome to this manufacturing process technology part 2 module 34. We were talking about the tool electrode material selection and also the dielectric material in an EDM process. So, the first thing which needs to be ascertained is that what kind of electrode materials are to be chosen for a successful EDM metal machining to happen, and most commonly used electrode materials are brass, copper, graphite, aluminum alloys, copper, tungsten alloys, silver tungsten alloys, etc. The method for making the electrodes are either conventional machining, that is something that one can think of directly, and these are particularly used for copper, brass, copper, tungsten alloys, easy to machine materials, even silver or maybe tungsten alloys, aluminum alloys, etc. Graphite is not that easy to machine, and so therefore there is some other method that can be deployed for depositing graphite on the surface of any other material which would give enough strength for sustaining the vibrations, etc., that are being imposed by the spark generation process alone. There is metal spraying and press forming, which are some of the other processes which are utilized for making tool materials or electrode materials. You also need to produce flow holes, so they are provided normally for better circulation of the dielectric, and these holes should be as large as possible for rough cuts to allow large flow rates at a low pressure. Regarding dielectric fluids, the basic requirement of an ideal dielectric fluids are really that it should be low viscosity, there should not be any surface forces of drag which would come out, which may change the orientation of the tools, particularly in thin tools. There should be absence of toxic vapors. By and large, the dielectric fluid should be chosen in a manner so that they are chemically neutral, they are not able to react to any other part of the supports or the tool holders, and etc. There should be generally a low or almost negligible inflaming tendency. So, that is one important point, because there are sparks which are generated, and although they are very momentary, if the ignition point is very low, there is a tendency of the whole thing to get inflamed, and that should not happen. Okay, and then obviously low cost again is a important criteria. So, there are many the dielectrics which are normally used, like kerosene, paraffin oil, silicone oil, etc. These are all hydrocarbon based materials which are preferable for this purpose, and the basic dielectric can also start from an ordinary water which possesses almost all these properties. Only thing is that in case of water, particularly when we are machining steel, there is an additional problem of rusting which may come out, and it may not be a very good choice. So, that is why one shifts to hydrocarbon oils rather than water. So, there is another issue about water, that there is always a potential difference between the tool and the workpiece in EDM, and so obviously it is all about what is the conductivity level of the water. If we are using plain water samples, if the conductivity of water is higher, then there is always a tendency that there would be a electrochemical machining process which would start happening, and this may lead to some kind of a tool distortion or the workpiece distortion, which is highly undesirable as far as the EDM process goes actually. So, therefore, it is preferable always to get this hydrocarbon based EDM material as a dielectric fluid. Let us just look at another aspect before we close the EDM topic, and that is about the effects of EDM on metal surfaces, particularly the hardness and how that gets affected because of the machining process. So, whether it is mechanical machining or any other kind of machining, there is always a tendency to have a super hardened region, which is because of we could say strain hardening on the surface of the material, because it is a peeling process in conventional machining that we are looking at. EDM also, because there is a tendency of the material to be melted and redeposited, and there is always a hardness issue which would come up, and we need to look at it in more details as to how the hardness changes because of such spark machining and high temperatures. So, the high temperatures generated by the sparks causes melting and vaporization, as you know, and melting and vaporization of the metal and also resolidification would definitely affect the properties of the materials which are close to the surface. Maybe we can call them the shallow layers, okay, of the machined surface. So, outermost layer is obviously rapidly chilled, and so it would be definitely very hard because of the quick annealing, and because of this quick chilling action, there is always a tendency of this material to be very hard. If you may remember the temperature transformation TTT curves as illustrated in part 1 of this course, we had mentioned there the quick formation of the martensite state which results in hardening. So, we are also machining steels here. So, obviously this rapid chilling or rapid cooling would result in this kind of hardness. Obviously, there is going to be a layer below this hard layer which is somewhat tempered in its condition, and if I look at the profile of a in case of a roughing EDM operation, and by roughing we mean a very high spark energy, we can see that the hardness suddenly if we look at it as a function of depth. So, on the surface the hardness is pretty good, pretty high, it is in the range of about 60 Rockwell hardness, 60 HRC, and it goes down all the way to about 100 and at a depth of below about 125 microns on the surface, where the hardness really is an all time low, which is probably about 25 HRC. So, from 60 to 25 HRC, and this could be actually as a result of the fact that just adjoint to the rapid chilled layer is a layer which is also supplying the amount of carbon which could really lead to a martensitic state formation on the top layer. So, this is a lot of a buffer layer, you could say, where there is it is a carbon provider for martensite to get generated on the top layer, and then obviously as you increase further, these layers are more or less in a tempered condition. The roughness just gradually changes up till it goes to almost a stability of near about 30 to 32 Rockwell hardness. So, the work material normally would have hardness of about 31 to 36, and so the remaining area is really not very important to be considered, but the sudden down grading of the hardness of a layer which has a complete martensite state and a layer which is like a supply layer for the excess carbon for the martensite to happen. Okay, these are the two important states which need some discussion. For a finishing process, because the spark energy already is very low, it is clear that such hardening is not a prominent feature, because we are not really superheating or anything the material. It is only just a few atomic layers that we are trying to move out by such processes, and so therefore the outer layer in this case is tempered and the hardness is low. Okay, and in this case the beyond a few layers of the top, the shallow layers below the top surface are really tempered and the hardness is low. So, the hardening of the surface layer during the EDM operation obviously would impart a better wear resistance as far as the roughing process goes, and because the hardness changes. However, the overall fatigue strength would reduce due to micro cracks, and that develops during rapid chilling process almost always, whether it is a casting process or it is some kind of a heat treatment of the cast or a forged part, etc., that we had discussed about earlier in the material properties section. So, with this I would like to close on the EDM topic and start a new machining topic which is about E-beam machining. E-beam machining is again deploying electrons or fast moving electrons, but the process of the spark machining has been electron sudden release because of a change in potential and also the dielectric breakdown. In this particular case, in E-beam process, it is a continuous source which emanates electrons at high velocity, and these electrons make a momentum transfer at the surface where they are hitting, which would result in a bond vibration or a change in the overall temperature of the surface where the electrons hit. So, let us talk about this process in some details, E-beam machining. So, it is obviously another thermal process where the agent which is doing the heat transfer here is the electron beam. There is a stream of electrons in fact of high speed which impinge on the work surface and transfer all their kinetic energy to the work material, and this produces intense heating and sometimes melting or sometimes even vaporization. So, obviously depending on the intensity of the heat generated, the material either can melt or vaporize. In this case the intensity also goes to an extent where some of the material can actually get vaporized, so sublimates directly. The process of heating by an electron beam can generally depend on the intensity of the beam, okay, and it can be used for various operations, for example annealing of the work surface, welding of two different parts together, or even metal removal operations. And in fact nowadays e-beam with the softer energy is also used for doing a lot of resist processing at a micro nano scale. In fact, if you may remember during the first section of this particular manufacturing process technology, we took you across process of e-beam lithography, which is also known as the nano imprint lithography, and also nano imprint lithography which engaged in fact the e-beam based photoresist processing. So, very high velocities can be obtained if you use higher voltages. For example, an accelerating voltage for the electron beam of about 150 kV would produce electron velocities which are almost near the speed of light, about 228,478 kilometers per second. Since an electron beam can be focused to a point by magnetic fields almost as narrow as 10 to 200 nano micrometers, and in fact this limit has gone down further these days. The power density of that particular point can go up almost to the level of about 6500 billion watts per millimeter square. So, such a power density obviously can vaporize any substance which comes in contact with it immediately. In fact, what happens in e-beam is that when the high velocity electrons are being moved to a surface, there are few surface layers which do not even register that there is fast moving electrons coming, and in fact the machining process starts at beyond certain surface layers. It starts from a certain depth where the momentum is being felt and the impact is being registered as a bond vibration or a increase in kinetic energy. So, e-beam is therefore nothing but a precisely controlled vaporization process in which the material can evaporate real quick. Let us look at some of these different processes around the hotspot diameter that they may generate and the power density that we are talking about. So, we can think of electric discharge in the very left corner of this particular plot here. The hotspot diameters are typically in the range of about 10 microns, and the power density goes as high as about 10 to the power of 7 watt per millimeter square. The lasers again would give a hotspot of between 10 and 100 micrometers. Hotspot side is more, and power density is slightly lower. It is probably in the range of somewhere around 10 to the power of 5 to 10 to the power of 7 watt per millimeter square. There is also another process of let us say welding arc or gas flame which generates really a high hotspot size. It could go about 10 to the power about 5, almost close to 10 to the power of 5 micrometers, about 0.1 meter, and it can have very less power density in the range of about 1 to probably 10 or 15 watt per millimeter square. Similarly, in case of welding, the hotspot is slightly lower, maybe 10 to the power 3 to 10 to the power 4 microns, but the power density is slightly higher, which is in the range of about close to about 90 to about 10 to the power of almost 10 to the power of 4 watt per millimeter square. What is interesting here is the e-beam process, as you can see, which can offer a variety of different power densities as well as hotspot sizes. So, that is the reason why e-beam is preferred process for even things which welding cannot do, or at a even like joining processes or cutting processes. So, e-beam obviously is that way a much suitable process for drilling fine holes, cutting narrow slots, whatever can be done with welding arc or a gas flame can almost always be done with e-beam machining. So, holes with the diameter of about 25 to 125 microns can be drilled almost instantaneously in sheets of thicknesses up to 1.25 millimeters. This is the power of e-beam. Narrow slot which has been cut by e-beam has a width of about 25 microns. We are talking about an e-beam which would be very effective. I am not talking about soft resist processing here, but about metal processing mostly. So, here is where it can go up to about 25 microns. Moreover, an electron beam can be maneuvered, and maneuvering can mostly take place because electrons which are moving, fast moving, they face Lorentz forces through ambient magnetic fields. So, if you have magnetic deflection coils, they are able to deflect and raster the beam typically over the surface. And so, you can actually go for machining very complex shapes and contours when we talk about such magnetically assisted electron beam movement. However, to avoid collision of accelerating electrons with air molecules, you need typically apply vacuum columns in which this electron beam processing can be done. So, the workpiece therefore is quite limited in its size, which is limited by the vacuum column. It is very expensive to evacuate a column in fact, and the vacuum levels we are talking about is about 10 to the power of minus 5 millimeters of mercury. So, to indicate the wide range of applications of e-beam, you can probably look at this power plot and decide for yourself that compared to the processes like electric discharge, laser beam machining, where we are wanting to place electron beam really. In comparison to other for thermal processes, it really has a very wide range, power density and hotspot diameters. So, let us look at how e-beam is produced and what is the basic principle of generating a fast moving electron beam. So, it is basically the thermionic effect, and it starts with a hot tungsten filament. So, you have a hot emitting electron emitting hot tungsten gun or filament which is the basis of starting the electrons, and then there are series of either series or series of perforated anodes, you can say, where there is an acceleration quickly to the electrons, and also there is some absorption which is generated. So, this is a perforated anode here, and then further there are electromagnetic lenses, and this controls the shape and size of the beam, and also there are beam control lenses. Once the size has been optimized and a certain diameter has been hit at or a focus has been hit at, you could actually raster this beam in a small zone around by deflecting the magnetic forces which are being applied in these guns of both directions, and so you could do beam rastering, and this is really the workpiece which we are talking about. So, the beam is shaped by a grid cup which makes sure that the beam actually is like more like a self focusing beam, as you can see here. So, these are the cathodes really. So, you can have sort of deflection cathodes, so that you can actually have the beam shape up into a small orifice. So, in case of drilling holes, the hole diameter depends on the beam diameter and the energy density that you are plugging in, and this accelerating voltage here which really depends on the cathode anode difference of potential. So, this is the beam accelerating voltage. This is a very critical component which determines what is the level of machining or what is the extent of machining that can happen the electron beam that has been produced. So, obviously, when the diameter of the hole is larger than the beam diameter, so the beam has to be deflected in a circular path, so that the whole radius can be machined on the workpiece surface. So, most holes drilled with an e-beam are characterized by a small crater on the beam incident side of the workpiece, and when such holes are continuously being drilled, you have a through hole and you can have a e-beam drilling process. So, the drilled hole will also possess a short taper in this particular case, particularly because of the fact that the beam also narrows down and there is something like a focus, beam focus which is hit upon, and that is somewhere at the depth where up to which the cutting has to happen really. And so, for doing this you always have this tendency of about 2 to 4 degree taper whenever you are using a sheet thickness more than about 100 microns. Okay. So, anywhere above 100 microns you will definitely get a taper in the hole that you are trying to drill. So, these are some performance parameters about the drilling of holes with different workpieces, like for example, if you are drilling in tungsten, stainless steels, aluminum, alumina, quartz, you have different workpiece thicknesses, hole diameters, drilling times, accelerating voltages and beam currents which are being given in this particular illustration, this table. So, you can see the very high accelerating voltages which have to be hit upon for drilling not very high thicknesses in the range of 2.5 mm to 1 mm, okay, and you have excessively high drilling time, which is in particularly stainless steel, it is about 10 seconds for drilling about 2.5 mm workpiece thickness. So, if you compare it with the conventional drilling, you can find out how much more energy will be consumed in drilling this, but obviously because such processes are meant for extremely complex contours or shapes, or even to some extent the alloys which are otherwise hard to machine, therefore you can still consider EBM process, although it is energy expensive in comparison to conventional processes. So, material like alumina for example, which is very hard, can be cut with a higher drilling time. Okay. So, 0.75 mm workpiece thickness is cut in about 30 seconds, and there you apply almost a beam current of 60 and a accelerating voltage of 125 kV, which makes it about how many watts. We can just check this. So, 125 times 10 to the power of 3 times of 60 times of 10 to the power of minus 6. So, this makes about 7.5 watts of power. So, reasonably good power that you are using for cutting a small 0.75 mm or 750 microns thick alumina workpiece. So, that is how you can characterize the various performance related parameters with respect to the beam process. While cutting a slot, the machining speeds normally depend on the rate of material removal. So, obviously we have to have some parity between what is the rate of material removal, so that we can fix up what is the beam scanning speed. Okay. So, this is more so important whenever we are doing or processing on diameters which are much larger than the beam diameter, where it necessitates the beam to scan over the surface to remove the whole material from the surface. So, the sides of a slot in a sheet with thickness up to 0.1 mm are almost parallel, and a 1 to 2 degree taper is observed in a slot cut with a thicker plate. Anything above 100 micron, as I had earlier told you, had almost always have a taper of 1 to 2 degrees. There is also a small amount of beam splatter which would occur particularly on the beam incident side, and this may result in some kind of a resolidification sometimes of the vaporized or molten material. The tables here give some idea about the slot cutting capabilities of E-beam. For example, if I have a workpiece thickness of 0.175 millimeters and a slot width of about 100 micrometers, I would typically have at an accelerating voltage 130 or 50 beam current, 50 microamperes beam current, 130 kV is accelerating voltage, would have a cutting speed of about 50 millimeters per minute. Okay. So, it is not really a very big speed of cutting as far as some of the other processes on the conventional side go. Similarly, for tungsten, brass, alumina, you can have various cutting speeds ranging from 125 millimeters per minute to about 50 millimeter per minute for brass, and for alumina it could be as high as about 600 millimeter per minute. Obviously, these are corresponding to different thicknesses. As you can see here, the tungsten plate that we are removing at a higher speed is about 0.05 millimeters, about 50 microns. Similarly, or 5 microns, I am sorry. Similarly, about 50 microns. Similarly, brass, this is about 250 microns, about 5 times thick than tungsten. So, what we are referring here is basically the range of cutting speeds that could be obtained for various thicknesses and various slot widths, as can be seen with E-beam machining. So, the other small issue is about, if there is some relationship that would happen between this beam power, which I just calculated some time back, as about probably 7 or 8 watts power, with respect to maybe the material removal rate. And so, such a correlation does exist empirically. It has been found that the power requirement is approximately proportional to the rate of the material removal, and is basically represented as P equal to CQ. This is only a very first estimate, you could say. I will actually show you a little different model in some in slides to come, where we will be talking about a slightly more accurate version of this P equal to CQ model. So, this is only a first estimate or a guesstimate, you can say, of the power. So, C is sort of a proportionally constant, which has been calculated for different materials like tungsten, iron, titanium, aluminum, and this is with respect to what is the power needed per unit material removal rate. The power is in watts, and you can see some of these values. Let us look at a small example problem here. Let us say if we have to cut a 150 micron wide slot using E-beam, and we are cutting that on a 1 mm thickness of a tungsten sheet, okay, and a beam power of about 5 kilowatts is used in this particular case. We have to determine what is the speed of cutting. So, let the speed of cutting be V, millimeters per minute, and we need to calculate the material removal rate with V millimeters per minute speed. So, we are cutting a slot which is about 150 micrometer in width. So, this is the width of the slot, and we are also cutting thickness of the sheet equal to 1 mm. Okay. So, obviously, if we looked at Q, the material removal rate, it will be the thickness of the slot that we are cutting. You can multiply this with -3 to have the corresponding number of mm's. Okay. So, 150 microns or 150 into 10 to the power -3 millimeters into 1 millimeter, that is the sectional area, times V millimeter per minute. Okay. So, this becomes so many mm cube per minute, okay, and the corresponding beam power therefore will be given by P equal to, let us say, C for tungsten, material used is tungsten here, which is being cut times of Q. So, the C for tungsten is borrowed as 12 watts per millimeter cube per minute times of the number of millimeter cube per minute actually predicted through the estimation in this earlier step here. So, since the P is given to be about 5000 watts, that is how the beam power is. V becomes equal to 5000 divided by 12 10 to the power or 12 into 0.15 millimeter per minute, and so you can see here the scan rate is really about 2778 millimeters per minute of about 4.6, you can say, centimeters per second. So, that is how the beam scan rate can be. So, this speed is only a guesstimate, okay. And we will see in following modules that this is quite low than the actual speed. So, we will try to do some dimension analysis, and we will try to see if we can get an accurate version of the actual speed with all these different parameters like thermal conductivity of the workpiece, or the beam temperature, so on and so forth, which comes at the melting point of the material, so on and so forth, which comes together in a more consolidated and analytical form. So, with this I would like to close this particular module, and in the next module we will talk a little more about e-beam processing. Thank you and goodbye.